We've mentioned in the previous videos that the quantity of gas is measured in moles, it's given the symbol N, so we need to be a bit clearer about what a mole actually is. Now the mole is one of the SI units, is one of the first important things to state. So it's one of the 7 SI units, and it deals with quantity. Not quantity of gas specifically, but just quantity in general. It's defined as being the number of defined as the number of atoms of carbon, or number of atoms, let's write it this way, number of atoms in 12 grams of carbon 12. So basically we're saying that if you have a sample of carbon 12 that has a mass of 12 grams, you will have 1 mole of particles. So that means that 1 mole is equal to 6.02 by 10 to the 23 particles. That particular number, 6.02 by 10 to the 23, is usually denoted as an N with a subscript A. And that value is known as Avogadro's constant. Spell that right. Avogadro's constant. So it's the number of particles in that equates to 12 grams of carbon 12. So when we're talking about 1 mole, we're really just talking about a number. So some comparisons that you might want to sort of think about here is that 1 dozen is 12. So 1 mole is 6.02 by 10 to the 23. It's just a number, or pi is 3.1415. So it's a number that represents a particular quantity written in a shorthand notation. So it also then leads us to this idea of looking at the quantity of gas. So N is then going to be equal to the number of particles in the gas divided by the number of particles in 1 mole. So that again is an equation in the data booklet. I'll just notate that in more detail. So N is number of moles, or the quantity measured in moles. Actually, I'll write that instead. Quantity in moles capital N is the quantity, the number of particles and finally N with subscript A is Avogadro's number. Now you'll see in the data booklet that Avogadro's number is actually stated as 6.02 by 10 to the 23 per mole. So basically it means that there's 6.02 by 10 to the 23 for every 1 mole of substance that you've got. So fairly straightforward calculation. It's just a ratio really. If you were talking about, say, 2 dozen, that's 24, so 24 on 12 gives you 2 dozen. So it's a simple calculation. You shouldn't really lose sleep over that one. It's very straightforward. What that does allow us to do, though, is start to look at relationships between moles and mass. So looking at molar mass is the next important step. So when we're dealing with substances, when we're looking at quantities in moles, that's a pretty a difficult thing to measure. You can't exactly just go and quantities in moles are difficult to measure. We can't really just go and count how many particles of gas there are in a container. We can't see them easily, for one thing, and the quantity that you would have to count there is a bit ridiculous. So 10 to the 23 particles, there's no way that you'd be able to count that. On the flip side, though, mass is quite easy to measure. So if we're looking at measuring the quantity of gas, we can just place the container on a set of scales, measure what it is when it's got the gas in it, take the gas out and measure what it is without the gas, and then you can find what the mass of the gas would be. So that if we then know what the mass of 1 mole of the substance is, so the mass of 1 mole is known as the molar mass. And that quantity of molar mass, we know what those masses are for elements, and so we can then start to combine them a little bit more easily. As an example there, using the definition that we saw earlier, 1 mole of carbon-12 has a mass of 12 grams. So its molar mass is, so that leads to the molar mass of carbon-12. So it'll seem like a bit of a strange way to state it. So molar mass of carbon-12 is 12 grams per mole. So that means if we had 2 moles, then the mass would be 24 grams. If we had 3 moles, the mass would be 36 grams. So 12 grams for every mole of gas that that you have in the container. Again, this doesn't just apply to gases. It applies to any substance that you're dealing with, but we're specifically looking at gases, so I'll keep using those as examples. If we're then considering the molar mass of certain substances, so things like say oxygen gas or water vapor, we can actually combine them if we know what the chemical components are. So when considering molar masses of substances, it's simply a case of adding the molar masses of the constituent parts. So I'll just have a look at a couple of easy examples there. So we'll start off first of all looking at so the molar mass of hydrogen. So of hydrogen atoms. So notice specifically looking at just the hydrogen atoms by themselves, that would be a molar mass of 1.00 grams per mole. The molar mass of oxygen atoms is 16 grams per mole. Kind of makes sense. Oxygen being a larger molecule, a larger atom, has a greater molar mass. Now, if we start to then sort of look at some gases, the molar mass of oxygen gas, so if we oxygen gas is not just individual oxygen atoms, it's actually O2, so 2 oxygen atoms bonded together. So when we're dealing with oxygen gas, we're actually talking about a molecule. So that means that the molar mass of oxygen as a gas is 2 lots of 16 grams per mole. So it gives us a molar mass of 32 grams per mole when we're looking at oxygen gas. Likewise, if we were looking at the molar mass of water vapor, so water vapor being H2O, so that's going to be 2 hydrogen atoms and 1 oxygen. So that means that its molar mass is going to be 2 of the hydrogen plus 1 of the molar mass of oxygen, so that gives us a total of 18 grams per mole. So So the last useful thing we need to talk about with molar mass is that we now have an easy way to relate the mass to the number of moles. So if mass and molar mass of a substance are known, so let's say we've got a balloon that's full of oxygen gas, and we know what the mass of that balloon is. We know that the molar mass of oxygen gas is 32 grams per mole. We can then figure out exactly what quantity of gas is in there. So the quantity can then be found. And this is really just a ratio problem again. So I'm going to write an equation that you could use if you wanted to. I know Dr. Livingston's a fan of not using this equation and just going with the ratios, but I'll just write it down. It's not in the data booklet, I don't think. So N is the quantity in moles, and so here it's quantity of gas particles, so it's not the atoms, it's the particles of the gas, measured in moles. M is the mass in kilograms. And we should express then the molar mass in kilograms per mole. Quite often you might come across expressions of molar mass as grams per mole, as I jotted down above. So you can, if your mass isn't measured in grams and your molar mass is in grams per mole, then you can have the mass here could be expressed in grams, and that would mean that the molar mass would need to be in grams per mole. So that's one of the reasons why it's a little bit, if you can sort of just work with the ratios and deal with the fact that if you know the molar mass of oxygen gas is 32 grams per mole, then you can easily identify that if you've got 3 moles, then you need to multiply 32 by 3. If you've got 10 moles, then it's going to be 320 grams. So, like I say, again, not a particularly complicated relationship. It's just common sense, really, if you sort of stop and think about it for a second. So there's the quantities relating to gases and moles and molar mass. We'll now have a look in a bit more detail at what the ideas are behind gases and how they behave and why these properties come about from the motion of the gas particles themselves.